Hello, can you see my screen now? I hope
yes,
so.
You make a full.
Yes, yes. Yes.
Okay, very nice.
So
Mary Paul Lombardo with the talk, Phases of Strong Interactions, the Lattice Approach. Please start.
Thank you. Good morning, everyone. Thank you very much, Vitaly, for the introduction, and thanks to you and the other organizers for having me here at this very, very interesting meeting. So my assignment was to tell you about what the lattice can achieve in this field, in the study of the phase diagram of strong interactions. I was a bit unsure how to organize the talk, whether I should perhaps pick some more important topic and try to give details. But also at this time, we are just finishing the paper with a bunch of colleagues from European Network. And our goal was exactly in writing this paper to give an overview to the community of what the lattice can do. So that's exactly somehow the same idea. And so I'm sort of giving rather general overview of all the activities on the lattice which have to do with the phases of strong interaction. And of course, I'm very grateful to the co-authors that I hope you will see in the paper when it appears. And of course, I will quote and credit especially young people whenever appropriate during my talk. So since we are discussing phase and phase transitions, so let me start from the very beginning, from the Lagrangian of strong interaction and from its symmetries. So this will basically everything discussed in this talk is based on this Lagrangian, and with also sometimes external fields of temperature, of chemical potentials for conserved charges, and temperatures and magnetic fields sometimes. Just to obviously remind ourselves, so in this talk, I will consider the number of flavor as a variable. Mostly I will consider 2 and 3 with some small comments of large number of flavors. The masses, of course, will be flavor dependent, although here is not explicitly indicated. And we will consider the presence of the theta term, especially in relation to the possible existence of a QCD axion, which is a candidate for dark matter. Now, with the zero mass, with all the masses are set to zero, the light quarks, there is independent, so right and left quarks could be independently rotated with UN. And so the global symmetry of the classical Lagrangian, just UN can be indicated as UN left cross UN right, which may be decomposed, as we often do, in simple unitary symmetries plus U1s. And then we know there is a U1 of baryon number, one is associated with baryon number, it is always conserved, even with, so it won't interfere with the other symmetries. It will only be broken if we explicitly introduce, if we do it by hand, by introducing a chemical potential. But even if we do so, this won't touch, of course, this other chiral symmetry. We know that the axial symmetry is explicitly broken always by quantum fluctuation, and we know that this chiral symmetry is also explicitly broken in the maximal attractive channel, originating this n²-1 Goldstone boson in the massless case, or pseudo-Goldstone boson in the massive case. And so for this breaking, we have an experimental evidence, so we trust this breaking because experimentally we observe the spectrum of the light mesons, the pseudoscalar light mesons, in accordance with the prediction of chiral perturbation theory associated with this breaking. And we know that the axial is explicitly broken instead because the eta prime mass doesn't follow. Instead, there is not a pseudo-Goldstone boson. So this knowledge of pattern that comes from experimental evidence, and it is also explicitly confirmed by many lattice calculations at zero temperature, which again follows chiral perturbation theory, and by also effective models and many other studies. So we trust this. So in a nutshell, the kind of phenomena that we want to address on the lattice is the restoration, is the fate of these symmetries with temperature. When discussing phase transitions here and also pseudo-critical points, I will really think about of chiral symmetry restoration. So from the point of view of field theory point of view, and we are a bit reluctant to really talk about confinement. We will base our analysis and discussions on the existence of all the parameters which we don't really have for light or medium light quarks for confinement. So most of the discussion has really related with the pattern of chiral symmetry and the pattern of and the spectrum of mesons. But of course, confinement is extremely important topic, and conceptually probably we know the most important open problem probably of strong interactions. So the topics I would like specifically to talk upon, to talk about are the thermal phase transitions and critical points, so the genuine critical points that we have in this phase diagram, and that will require considering setting to zero the light quarks to have an exact definition. Then I want to say what we can say once the quarks take their physical values. And so I want to discuss the nature of the quark-gluon plasma, so what we have achieved so far, and especially what we can pass on to our colleague in phenomenology and in experiments. So which kind of information we can provide in the physical case. This can be done, and so this will be on the positive side, but then I also like to discuss some methodological challenges. So what we cannot do. So there are problems on the lattice, it has been already mentioned, this sign problem that we will discuss and try to highlight the two main lines of activities in which the sign problem has an impact. And this basically the physics of real time, which has to do with spectral functions, and the physics of high Byron density. Now, let me pause at this point, so I don't give you an introduction, a technical introduction to lattice. The only main technical point that we should keep in mind is that calculations are being done in Euclidean time. So one has done in order to formulate the theory in a way which is good and convenient for numerical evaluation. For numerical evaluation, we have to rotate the time from Minkowski to Euclidean, and then has an impact on the possibility of doing calculations in real time, of course, as I will review when we get to this point. Then I will say, having stated the problems that we encounter, I'd like to say, nonetheless, whether we can say anything when the matter becomes really very dense and very cold, so we don't have anymore the help of fluctuations to facilitate the access to this dense matter. Finally, the last topic, I want to go back to zero chemical potential, but to very, very high temperatures when there was a freeze out of hypothetical axions, and then I will discuss whether if this freeze out indeed happened in the journey of the universe coming back towards the quark-gluon plasma transition, and then axions at this point will be here with us as a cold gas, and then which kind of consequences we may have on their masses from the QCD dynamics. So I will present the limit that the lattice community has found on the QCD axion mass after doing thermodynamic calculations of QCD on the lattice. So this is the scheme. Let me start with the scheme. So this is the same short diagram that I drew before, but now we have to think now. Anyway, I will discuss first the case of the massless up and down quark. But just to simplify and not to say it too many times, so the strange quark here is fixed to its critical value. This, it doesn't really matter. So when I consider the symmetries of QCD. So if I consider M, if M is just a mass of a strange quark, but I keep massless the other two quarks, I still have the SU2 cross SU2 symmetry, which is not spoiled by the presence of the strange quark. So I can consider here, make a discussion in the massless up and down limit and discuss SU2 cross SU2 symmetry, or in isomorphic language and O4 symmetry, even if I have a massive strange quark. Because of this, if I switch on the up and down quark, when up and down then are their physical values, here I represent a situation in which is really physical QCD. So up and down quark on this dotted line. So when up and down and strange have their physical values. Now, the charm quark doesn't participate at all in the current dynamics, so we can ignore it altogether, at least around the critical temperature. Above, it may change. So, in the massless case, I do expect a genuine critical point. This would become a pseudo-critical point here when the masses of the quark are switched on. The standard law, the most standard expectation, which we have also seen before in the very nice talk by Irina, she was showing the Columbia plot drawn following the standard expectation that I have a critical point here in the universality class of an O4 magnet with spontaneous breaking to O3, and then in 3 dimensions because we are at finite temperature. So this is the expectation here. And as we have said before, the chemical potential, even if I switch on the chemical potential, I'm not spoiling and I'm not interfering with the symmetries with the chiral symmetry. So this O4 behavior may well persist even at finite chemical potential. And now the question that we will finally ask is which is the imprinting of this critical behavior, whether this critical behavior persists up to which is the signature of critical behavior persisting in the physical up and down mass, and also which is the fate of this critical point that has been already introduced. So suppose that I accept the fact that I have an O4 critical line here, but I know that a high chemical potential, all models and also general physical intuition is telling us that I should expect a strong first order phase transition. So I have a first order line, a second order line, which are meeting somehow at the tricritical point here. Once I switch on the mass, the tricritical point will finally turn into the critical, the famous critical endpoint of QCD, this point here that everyone wants to find, but we haven't found yet. What's very interesting in looking at things in this way, and I think this observation has been done first by hot QCD in a study in context of lattice studies, what's really very interesting at this point is that the critical endpoint, so if this plot is correct, the critical endpoint will, the temperature of the critical endpoint will certainly be below. It will happen in a colder, much colder than the critical temperature in the chiral limit. So in this way, with this, if we accept this critical scenario, we will have a critical endpoint. This poses a constraint on the position of the critical endpoint, at least. And this is important because we are not able somehow to find the critical endpoint. It's difficult. I will show you the results. And then having a bona fide upper bound is certainly very interesting, also as a guidance for experiments. So this is why it's so useful to confirm this scenario, besides its theoretical relevance. Now, as I said, this is a standard expectation, which comes from the very old work by Pisarski and Wilczek. But it is actually, there is really more than this, and the scenarios are more complicated and varied. And after all, we have to accept that we don't have any real theoretical guidance from this effective analysis. Because first of all, the process of chiral symmetry restoration and the nature is very much entangled with the fate of the axial symmetry at the transition. So if axial symmetry remains strongly broken, then the whole process is driven only by the O4 to O3. And then for two flavors, I have the most natural possibilities, this second order transition, but also could also be a first order. This is pointed out by more recent work following Pisarski-Wilczek by these people. So although it would be very unnatural playing with the coefficients, but still a first order coefficients cannot be completely excluded, although nobody has really seen it. But indeed, if U1 is restored, Pisarski-Wilczek proposed the first order in that case, but it would also be possible different scenario. Again, even a second order transition possible. So in conclusion, there is no real prediction. Even more interesting, once I approach three flavor, again, a standard law from Pisarski-Wilczek would be first order transition, but this has been challenged by recent numerical work by Ove Phillips and Francesca Cuteri and Filippo Sciarra. And indeed, they suggest that the transition may remain of second order all the way to the conformal window. And that would be a completely change of views and revolutionize indeed also our Columbia plot. It will look totally different. So that's really point for discussion, I think, which would be the implication of such modification. So where do we stand? I mean, there are enormous amount of results, so let me just summarize. So the critical temperature has been estimated at least by two groups in the chiral limit. This is what the hot QCD finds, and this is my results with Andrei Kotov and Anton Trunin, and we substantially agree. It's a rather low critical temperature. The pseudo-critical temperature has been estimated long ago by the Wuppertal Budapest and then confirmed by hot QCD. So these two numbers are more or less okay, but in both cases for this estimated, we agreed that we are indeed using the O4 extrapolation. So these two groups, we both agree that O4 universality class works for very small quark masses and two flavors. And this starting from the physical biomass. And because of this, we can extrapolate with confidence. But if this is not true, this number may change. So there is some input behind that. But assuming that this is correct, this is what we get. Now, how large is the scaling window? This, what we have found is that an imprinting of the O4 scaling still remains true in the physical case, and also up to temperatures of 300 MeV. That looks quite unnatural. So one would expect that one forgets earlier about the scaling. And again, this suggests some topic for discussion, but this is the result and the observation. Now, what happens if I move to three flavor? That would be the bottom left corner of the Columbia plot. Sipats Sharma has new results with hot QCD, and she found the critical temperature in the chiral limit at around 100 MeV. It should go down with respect to two flavors, so this is correct. Of course, comparing theories with different number of flavors is not completely trivial. It assumes that one has a good ultraviolet common scale, but okay, assuming that we have done this, it goes down, and it does. There is no evidence for the first order phase transition though. So it remains a crossover, and there is no clear evidence that one has this expected first order phase transition. And indeed, this is somehow in accordance of Cuteri and Philipson results that for three flavor, the transition may remain of second order, and that would be really something really very interesting. So what do we have to do now? This is concerning the critical points. I will comment more on the genuine critical endpoint of QCD at finite chemical potential. But concerning zero chemical potential, we know that it's important to understand the chiral behavior in QCD because this constrains the phase diagram and the location of the critical point that I discussed now. It's also important to better understand the interplay of chiral and axial symmetry, and they have an impact on the nature of the phase transition. And of course, the fate of the anomaly has also an impact on the physics of the quarkulum plasma. There is some important and interesting discrepancy with functional renormalization group, which is an important approach, ab initio approach to the QCD dynamics, very successful. And we can't quite agree yet on the extent of the scaling window and then on the reliability of the O4 fits to extremate the critical temperature. This is, we don't know exactly where the disagreement appears. And we are indeed discussing with the Jan's group to try to clarify this point. Now, coming to the to phenomenological aspects, this is just to have an overview of the different experiments that are exploring the phase diagram. I don't want to discuss this, just to say that the smaller the collision energy, and the larger the chemical potential which is being explored. So if we don't find the critical endpoint in this scan, then these other experiments like CBM, HADES, MPD have perhaps a chance. I understand indeed, I don't know, I'm not sure, but that BNL people are really trying to start a serious collaboration with other experiments in order to maximize the chance of observing the critical endpoint. Now, the most important, one of the most important quantities which are studied on the lattice to see the quarkulum plasma, the properties of the quarkulum plasma, are fluctuations. And sorry, they are interesting per se as signatures of critical behavior, but also they are important because they allow the computation of pressure density and hence the equation of state. And of course are also natural input for phenomenological modeling. Now, equation of state is really doing very well in the sense, even at finite chemical potential. Here I'm picking one significant results, but the quality of this result is a guarantee also for the others. So this is the light quark density, and this has been computed by the Wuppertal-Budapest collaboration at a very large baryochemical potential, sorry, as a function of temperature. And the temperature, sorry, as a function of temperature, and then you can see still the temperature explored are still quite high. So you can't go basically below 120 MeV because exactly you need to reconstruct the phase, the pressure. You need to reconstruct the grand canonical partition function. You need you do it by using fluctuations. Now, if temperature is too low, fluctuations aren't strong enough, and so you need enormous accuracy to measure them. So fluctuations are really helping you in this game. And this is why we can explore finite density with high temperatures, but not with low temperatures, because at low temperatures, fluctuations are so small that in order to take advantage of them to move on the chemical potential direction, one needs enormous amount of computer time. But at high temperature, this is possible, and then the quality of the results are really good. So in a sense, we can offer, and the agreement between different techniques is quite remarkable. So this is doing very well. There is activity in the influence of magnetic field. It's not so immediately obvious how this information may be passed on to experiments, because the magnetic fields which may be responsible for chiral magnetic effect are very transient. Chiral magnetic effect has not been really observed in experiments, but from theoretical point of view, certainly very interesting. And the PISA group has new results still working. For temperature, they reach up temperature up to 98 MeV, observe first order transition as a function of magnetic field. They don't know well what happens again. Lower temperatures are more difficult. Important phenomenological effort, lattice combined with other approaches done by the best collaboration in the United States. I'm sorry, is this perhaps a bit disturbing? And the main goal, really, the clear goal of this collaboration is the search for the QCD critical point. So this is, first of all, as a sanity check of what they are doing. They study very nicely the crossover temperature at finite chemical potential, again, building on the knowledge of the fluctuations that they have. By studying this, they can reconstruct the pseudo-critical line that you see in this plot, and also maybe compared with different chemical freeze-out observed in experiment. This is an interesting ongoing discussion because, of course, you expect that the freeze-out happens below any pseudo-critical line, so the hadrons become hadrons again in the hadronic phase, and this apparently what happens, but still is interesting comparison to be made. And this line becomes, of course, the information that we can look here. We see confidence a zero chemical potential with small errors, and the error band becomes a little bit larger, of course, and we lose finally control when the chemical potential grow big, exactly because we rely on extrapolation in whatever way we want to do it, either from imaginary chemical potential or Taylor expansion or whatever, but still we rely on fluctuations, a zero chemical potential, and then they help, but not for a very long time. And here at some point we have to stop. If we trust the statement that any critical endpoint, if exists, should be below 135 MeV, which was the position of the critical point in the chiral limit at zero chemical potential. And then we can see that we are not really exploring the important region to measure the critical endpoints yet. This point has been seen, for instance, also in this more clearly. This is a compilation done by Jan Pawlowski. Is anyone speaking or asking questions? Or sorry, am I missing something?
Everything is okay. Please continue.
Okay, sorry. And this is a compilation of results from the lattice that we are here driven from different collaborations. So from Hot QCD, from Wuppertal Budapest is a bit here, this green. And what and this is a functional renormalization group from the group of Jan Pawlowski and probably with colleagues in Gießen. And also data from the various freeze-out of experiments. The critical green light is estimated, this bubble is where we may expect the critical endpoint of QCD. This is because, again, should be below 130. So basically, this is what has been done. And we know that cannot be too low because at some point we know there is this clear first order line, which has been also seen, I think, in nuclear fragmentation experiments or something. So we don't expect that low. And then we see that somehow the lattice studies haven't quite reached with confidence this domain. Of course, there is a continual attempt, but if I stick to these two approaches that I have shown you, so basically the simple Taylor expansion and the analytic continuation from imaginary chemical potential, where you really want to produce strong, reliable results, this kind of strategies doesn't get to the region where we expect the critical endpoint to be. So there is no prediction in this sense. Very important aspect in the understanding of the quark-gluon plasma are, of course, the transport properties, because they also enter directly in the simulation codes to interpret, for instance, in the hydro codes. And well, again, these are difficult, so let me quickly summarize. There are lots of very interesting results, but Please note here they say pure SU3 gauge. So the other results I was showing you were results with dynamical fermions, so in the physical point, but here still we have to use this very simplified theory. And this is because the transport is very difficult. You need very, very high quality data that at the moment you can only produce if you want to get to it. This is the famous eta over S, and this is the strongly coupled limit from duality, and the 1 over 4 pi, and you see it is being approached, so they are physically consistent, but the accuracy is not high, and for the challenges that I will discuss in a moment. And when we go at finite density for these transport coefficients, only model calculations are possible so far. So that's what's complicated. So what do we have to, what happens now for this phenomenological study? So we know a lot for small chemical potential. So basically here we are really in position, the community, to talk to experimentalists, to confront results, to put the fine. But unfortunately, we don't again yet extend to the critical point region. So this is the main issue to be further pushed. And the same is true for transport coefficients and spectral functions, which are related by the Kubo formula. This is really a field where phenomenologists and experimentalists work together. Again, this, for instance, this very nice discussion has been done by Olga with the supervision also of Elena Gratowskaja, I have to say, and so in the group of Jörg Eichelin. So it's really working together, lattice and experimentalists and phenomenologists very, very closely to understand. So now let's discuss about the limitation. So lattice QCD relies a lot on the interpretation of a Boltzmann factor as a density of probability. So once we lose the positivity of the action, then it's a problem. Then we know, and this is called the sign problem. So when this happens, well, first of all, if we want to stay with real time rather than imaginary time, so this is very clear because T appears in the actions, and when it comes back to imaginary, back to real, then the sign is oscillating. Chemical potential is less immediately obvious, but basically it has to do with the CP violation, with the time reversal violation, and then again, positivity is no longer guaranteed. So let's tackle these two issues one at a time. Spectral functions. So how do I get a spectral function? Are those objects which, when I have a stable state, are a delta function centered on the mass of the state. So we want to calculate the spectral function from the lattice. And the first step to calculate the spectral function are on the lattice 2-point correlation functions in Euclidean time. So I start with the Euclidean correlator, and the pole, a single pole Euclidean correlator becomes exponential decay. Or I start with exponential decay, I want to go back to the delta function in frequencies. When the spectral function becomes broader, exponential decay becomes something else. This is what we have to learn how to handle. Of course, from the point of view of spectral function, the reason why we really want to calculate them is to account for the sequential suppression, for instance, of heavy meson states. Maybe the less young among us would remember that one of the first historical signatures for the quark-gluon plasma was the suppression of J psi. So in the plasma, people measured the less J psi in CERN, SPS. And they say, oh, plasma is gone because it's not supporting J psi anymore. But then BNL found that J psi would survive instead, at least a little bit. And then the scenario of sequential suppression appeared. And now we better understand that, of course, these heavy mesons are bound mostly by Coulombic forces. And these Coulombic forces are very resilient. They don't disappear immediately because of temperature. And then it becomes, they say now, bothonium and charmonium are important thermometers of the plasma, because we can see how they sequentially melt first the excited states and then the fundamental state, but very, very high temperatures. So this is what we want to predict on the lattice. And then we find a qualitative agreement with this scenario. See, the scenario of sequential suppression is really supported, but no quantitative confirmation. So this is how we compute the spectral function on the lattice from Euclidean correlator, and then you see immediately why it's so difficult. It's an inverse problem in which I have to reconstruct a spectral function, so a function which has features, which has peaks from Euclidean correlator, which is smooth. And then, of course, the spectral functions are also essential to compute transport coefficients, so it's the same league, and that's why it's important for us to learn how to do that. And well, let me just reiterate that the results are satisfactory qualitatively, but not quantitatively correct. As for instance, the calculations you have seen from transport comes from this kind of equality, and it is only possible for quenched or Yang-Mills models with confidence at the moment. Now let's go quickly to one of the main interests is the search for the critical point. One strategy to find the critical point, since we discussed the series expansions, is which is the radius of convergence of the series. So what is limiting the radius of convergence? Well, wherever I have singularities in the complex plane, this limits the radius of convergence of the Taylor series. So if I can estimate the radius of convergence, I know that there is a singularity in the complex plane, though. So this doesn't necessarily correspond to the true critical endpoint of QCD, which has to happen for real chemical potential. So that's why one has to invent something to identify the critical endpoint. And basically, there are these two different strategies. One, again, is to study anyway the radius of convergence and try to understand where it is located. Indeed, if I know all the coefficients of a Taylor series with a great accuracy, I can also find, for instance, the direction in which the zero happens. I may rotate the coefficients in such a way they are all positive, indicating the singularity on the real axis. But accuracy is the name of the game here. I need many, many coefficients to make sure that what I'm doing is robust. The other alternative strategy, I try to reconstruct the grand canonical partition function modulo overall constant, and then this critical endpoint would correspond to a zero. Any singularity, any zeros in the grand canonical partition function would correspond to a singularity if happens at the real chemical potential. So these are of course related somehow. These two are related basically by a log. So if either I search the zeros of the grand canonical partition function, or I take the log and compute the pressure and the search for singularity of the pressures. But numerically, they make a big difference. So this is the best offer at the moment of the search for the poles, and they find for different temperature some indication of poles in the correct region, but as you see, the errors are still very large, should be further enhanced. That's very interesting. Of course, you may want to invent tricks to resum the series, convert Taylor series in Padé series, search for the poles of Padé. I mean, all this is just nice mathematical analysis, but you have to fight with numerical accuracy. Very interesting, and our discussion leader will tell us perhaps more about that, is the canonical approach is a very sound way to reconstruct, formally very nice and appealing, to reconstruct the grand canonical partition function once one has good data at imaginary chemical potential. So I can exploit the properties of holomorphic function, and once I have a number density for imaginary chemical potential, I can formally reconstruct the grand canonical partition function, then the canonical partition function. Having the canonical partition function, I then have the grand canonical partition function in the entire complex plane. So it's a very elegant approach. Again, it has to fight with accuracy, but results are already appearing, and they identify with confidence the Roberts-Weiss singularity in the complex plane, so a singularity that we know. So I would say that's very successful and and promising. So again, of course, it's very important to go beyond the important sampling, and this opens the way of communication with astrophysics and of compact stars, for instance, and collider experiments at lower energy. And then, of course, here it's very important to talk to mathematicians. I discovered that there is enormous activity in mathematics on numerical methods for inverse Laplace. I didn't expect that. I thought it was old subject, but people are still working hard, and maybe we have to learn from them. So now I'm sorry, in the interest of time, perhaps I skip cold and dense matter and say you a little bit, because cold and dense, we don't have any way for QCD, just models, so it's good for discussion. Here instead is real QCD. As we say, we can add, this term theta, we can couple the topological charge to QCD with this parameter theta. But we know that the theta is constrained experimentally to be very, very slow, very, very small, which is called the strong CP problem. It could stay small. There are also people who say it has to be 0, 0 and no room for axions. I won't discuss these more exotic scenarios. But accepting that it is really small, one way to account for the smallness is to set it to 0 dynamically by use of this pseudo-Nambu-Goldstone boson of an extra U1 symmetry, which would be broken at cosmological times. Now, this new particle, the axion, is also very good dark matter candidate. I have 2 minutes, right, Vitaly, sorry.
No,
or maybe...
You have 2 minutes.
Yeah, okay, thank you very much. Yes, so just to make sure. And also maybe a source of this Peccei-Quinn transition in certain models in which may be realized explicitly may really originate some gravitational waves too, which would be an indirect way to probe the existence of the axion. Now, the mass of the axion is related with the topological susceptibility, which may be measured in QCD just by simple effective field calculation. And then what we really want to know is how the topological susceptibility changes with temperature. And once we know that, we have the axion mass as a function of temperature, we can calculate the density of the axions at freeze out when the axion equals the Hubble radius, roughly inverse. And then from that, we can estimate the, after the freeze out, the axions would behave as a cold gas. And with these parameters at hand, we can put limit on the axion mass, knowing the density of quark matter today. So we say, suppose that all the dark matter today is made by QCD axion, how much the mass could that be? We need to carry out these calculations. We need to know the topological susceptibilities at very, very high temperatures, the temperatures of the freeze out. Only the Wuppertal-Budapest collaboration could reach up to this very high temperature with interesting tricks, but other people have to extrapolate. But it's also good because we extrapolate by using the dilute instanton gas. So in turn, we also check that the dilute instanton gas approximation is very good at high temperature. And these are the results, and these are the results obtained by different groups. Well, the agreement is not fantastic, but is decent. It costed lots of effort to build this agreement because initially the differences were much larger, but we all worked very, very hard. Here are my results with Andre and Anton and other people, colleagues, beautiful results by the Wuppertal Budapest famous Nature paper. You may say there are discrepancies, but we played a game here and we were searching for the impact of these uncertainties on the actual values, on the actual lower limit of the axion mass. And even with our most recent results on the axion mass, we find that the limits are quite robust. Even if we were exaggerating and say, okay, we are wrong by 4 orders of magnitude in the amplitudes of the fit, but remember that we work with this 4th root of the susceptibility. So the actual impact will not be so bad. So indeed, we have a lower absolute limit for the QCD in the simplest variant of the QCD axion mass at 20 microelectron volt, which is in the working region of most experiments. But it's important to give this kind of input because the experiments searching for axions, each experiment works in a rather limited set. And for instance, there is an American experiment which is sort of reconsidering a little bit the working region pushed by these lattice results, because the guidance from chiral perturbation theory or models was pointing towards much lower values. So that was, I think, interesting contribution that the lattice is making to dark matter and cosmology. So then, of course, we want to improve these results and get to study also the axion potential. So when we study topological susceptibility, we are only at the second momentum of the axion potential. So that's all I had to say. So we have lots of important connection with nearby field. We really like to enhance our communication with other fields, but we have also methodological bottleneck, which require internal discussion, lattice community. We are doing this. I am not discussing important future developments, but we may talk about it. Is of course something that the lattice is triggering. And so with that, I thank you very much. Thanks.
Thank you, Maria. Thank you very much for your nice and comprehensive review. Unfortunately, we have no time for short questions, so let's postpone discussion of the talk. No, very good, very good. It was very good. So let's postpone discussion to discussion session.